All right, we will continue with just looking at the critical points that go into setting up our equations in 2D, and I hope what you're noticing is that there is really nothing to do, nothing new at all, just paying attention to the fact that our spatial dimensions run over 1 and 2. Okay, so let's get on with this. All right, so we'd got as far as the boundary integral. Okay, the boundary integral, which is this one, integral over the Neumann boundary, WH Jn ds, right? And here we need to pay attention to the fact that ds is a curve, right? An elemental, right? An elemental curve. Okay, again, this is sum now over E belonging to the set of elements whose boundaries coincide with the Neumann boundary, right? And we'd use that notation, script E sub n. Integral now over partial omega E sub j, all right? And then the integral over that part of the element boundary that coincides with the Neumann boundary, okay? WH Jn d little s, okay? And then we said that what we need to do is worry about this integral. Okay, and the way we do this is to once again do a sum over A, and now we observe that we recall things that we'd noticed before, right? Which and one of the things we'd noticed before was that if this is our domain and this were the element that we were concerned with, right? What we note is that only some of the nodes lie on the relevant boundary, right? If this part of the boundary were the Dirichlet boundary, this part were the Neumann boundary, what we observe is that it's only this node A, or that degree of freedom, which belongs to the set of Neumann boundary nodes, which we called A sub n. Okay, and likewise, if right next to it we were to have a triangular element, and this is possible in a finite element mesh, right? If we had a triangular element right here, then it would again be, so that would be A, maybe that would also be B, also belonging to A sub n. Okay, all right, so we have A belonging to A sub n, C A E integral over, all right, now we need to go to the element boundary, but in the parent subdomain. Here we would have NA, Jn, okay, and what we would do is to recall for ourselves that if our edge here right, if our edge here were this one, right, partial omega E sub j, right? We would need to just remember that, well, it always arises as a mapping from one of the coordinate lines now in the parent domain, right? So what we would observe is that we have this map, okay, right? And that map, you remember, is something that we denoted as JS, okay? Okay, now in this particular case, the way I've written it out, Js is a function only of C2, right? So, okay, given that we know the positions of all the relevant degrees of freedom and actually the nodal coordinates in the physical domain, the relevant nodal coordinates in the physical domain are that one and this one. Okay, and the relevant ones in the parent domain are -1, -1 and 1, -1. Okay, so we know very well how to construct that map JS. All right. In particular, we did talk about in the case of the 3D problem, we said that if the edge were not in the physical domain, if the edge were not aligned with one of the coordinate directions, right, or one of the basis vectors in two-dimensional space, such as this case, right, that edge, partial omega E sub j, is not quite aligned with the E1 vector, okay? And I'd suggested back then when we were doing this in 3D that, all right, maybe we need to define a new direction there, right? Right, we said that maybe we need to define a new vector along that direction, okay? If that were the case, it would take a little bit of an effort to construct that, but not too much. If it did align perfectly with a coordinate direction, it would be a much simpler construction, right, to get this map J sub S. Okay. All right. So what one would get in this case is here we would get a determinant of JS, right? And we would be then integrating along for C2 as shown in this particular example. Okay, and the same sort of thing would happen if we had a triangular element. Right, if that were the triangular element, right, and that were the direction that we needed to integrate along, right, if this were, sorry, the edge that we needed to integrate along, it would come from a regular unit domain, okay. Those would be the nodes that would be relevant in this domain. If that were A, B, and if A were the first node in the physical element and so on, right? So then it would be mapped along 0, 0 and 1, 0. Okay? I just realized that for the way I've drawn things, this elemental curve length is dxc1, not dxc2. All right. So this is what we would have to construct. right? In either case, we would note that that determinant of Js is simply derivative of x tilde with respect to C1. Okay? If x tilde were one of the coordinate directions only, it would be a very simple calculation. It would be a little more complicated if it were aligned in some general direction, right, in some intermediate direction. Okay, but nevertheless it can be constructed. All right. Okay, and then this figure is quite busy now, but let me just do one more thing here. That integral is what I believe we were calling f a sub j, sorry, fj sub a. Fj a element E. Okay. All right. So we have all of these, and what we would then have to do is put these things together. Okay. One thing to point out is one useful thing to point out is that I will do in a remark here. Okay, is that for the case of linear triangles, okay, the matrix components of JC, right? JC is, for the case of linear triangles, is the map that allows us to go to the physical domain from the parent domain, right? And if we are working with linear triangles, JC takes on a very special form, right? So the map itself is x of C, and JC is the gradient of that map, right? So the matrix JC here, which is now x1 comma C1, x1 comma C2, x2 comma C1, x2 comma C2. If you go ahead and compute this for linear triangles, what you find is that this matrix is a constant. Right? The components of that matrix are constant because of the linearity of the map. Right? There's no bilinearity in the dependence of x1 and x2 upon in C1 and C2. So when you take those derivatives, you get constants. Right? And in fact, not only that, but a further simplification is the fact that the determinant of JC in this special case, right, only for linear triangles, turns out to be, can you deduce what it's going to be? It's always twice the area of omega E. Okay, measure of omega E is the area of omega E in this case. Okay, so that's a special case for linear triangles. It's something that's useful to know and to be able to use when one is developing these formulations. Okay? All right. So let's return then to assembly. All right? For assembly, here's what we have. Sum over E of let me see, we have here sum over A comma B, C A E, K bar A B, D B E, equals sum over E, sum over A, C A E, F bar internal A E, right? This is what we get from the forcing, plus sum E belonging to the set of elements that include whose boundaries coincide with the Neumann boundary, sum A belonging to A sub n, right? The set of nodes within each of those elements that also lie on the Neumann boundary, C A E, F bar, sorry, F j A E. There's no bar on that one. Okay. Assembly is what lets us go from here to a single matrix, right? And now actually everything's just the same. Nothing is any different. We first of all can get rid of the sum over degrees of freedom over in each element by essentially writing each of these sums using matrix vector notation, right? So we here introduce the idea of the row vector of weighting function degrees of freedom, right? We get k bar, the rectangular conductivity matrix for this element, multiplying d bar, and I don't need that superscript, multiplying d bar E, right? And you remember that the reason I'm using a k bar and a d bar is recognizing that the Dirichlet boundary conditions have a say here, right? That the k bar is a rectangular matrix because of the fact that the existence of the Dirichlet boundary conditions says that the size of the vector C E, right, is not the same as the size of the vector d bar E in every single case, right? For the elements lying on the Dirichlet boundary, they're not the same, right? And then likewise for this we get C E transpose F bar internal E, and here we get the same thing, right? Remember in this case, in going to the full row vector CE, we simply say that we construct Fj E such that the degrees of freedom that don't lie on the Neumann boundary from that element E will simply have 0 entries in the corresponding Fj vector. Okay, this is exactly the same, right? We don't, the way we did this in 3D and the way we would do this in 2D is exactly the same. In the case of 2D, we, like in the case of 3D, the sum over the degrees of freedom A and B, right, would run over the number of nodes in the element, right, or the number of degrees of freedom that were used to interpolate each field in that case. The fact that that number is greater in 3D and lesser in 2D has no effect, right? We just run over that sum. Okay, so that process is no different, okay, in constructing these element matrices and vectors.